Alright, so hello and welcome. Howdy. Feeling a little sad today, so we'll take this kind of slow, I guess. I don't even know, man. I don't know. I'm sad. I'm just sad. I don't even know. I don't know what to say. But there is a problem that I want to look at. We're not going to solve it. Probably not today. I'm like way too tired. I'm ready to just go to bed. Sad and tired. Sad and tired. Anyway. Given an input string S and a pattern P, implement regular expression matching with support for dot and asterisk, where dot matches any single character, asterisk matches 0 more of the preceding element. Yeah, it's asterisk, it's not ampersand. Okay. Okay. Matching should cover the entire input string, not partial. Input AA, P equals A, false. A does not match the entire string AA, P is A star, true. Star means 0 more of the preceding element A, therefore by repeating A once it becomes AA. So what's interesting is this is basically creating a small a DFA. We're just implementing the characters and the I mean, C++ has a regular expression library built in, right? Presumably they don't want us to just use it. Just use the regex library, done. No problem. Dot asterisk means 0 more of any character dot. AAB, see, this is called Kleene star, by the way. So it wants to support the wildcard, any character wildcard, as well as the Kleene star. True, C can be repeated 0 times, can be repeated 1 time, therefore it matches AAB. So 0, 1, 1, 1. MISSI, SSI, PPI. Mississippi. Get MIS more than any number of times, IS, S any number of times, P any number of times, then I with anything at the end. It's false. Whoa. Really? Well, 2 S's, 1 I, 2. Oh, I was missing an I. I see. Interesting. S length is 20, P length is 30, S contains only lowercase English letters, P contains only lowercase English letters. Dot and star asterisk is guaranteed for each appearance of the character asterisk. There will be a previous valid character to match. Guaranteed for each appearance of the character asterisk. There will be a previous valid character to match. Okay. What's interesting is it looks like we're not supporting parentheses, so this actually is relatively easy. No, I wouldn't say it's easy, but it's easier. So, yeah, basically, what you have is an NFA rather than a DFA, and each of those Kleene stars in the DFA is a deterministic finite automata. Each of the Kleene stars give you a loop back to your starting point. Now, what's interesting though is that you could do both. You can loop back, or to match the same character again, or you can go to the next state. And so this is a sort of end up creating a state diagram out of our input string P pattern. Create like create basically different states. and then we're going to actually just simulate the finite automata. I'm trying to think how we could do this. Excuse me. Well, can encode the finite automata if you wanted to as a really it would be like a graph. We don't have ors. Well, how do we do 0 more also? That's a good question too. Yeah, actually you do have, it's non-deterministic. I believe 0 more would give you something non-deterministic. Let me think about it. It's called an NFA. Excuse me. Well, technically you can convert your NFA to a DFA. I'm just thinking if there's a way to process our NFA. I think our NFA ends up being a like a depth first search type of thing to process the NFA. Trying to think of a different approach. Yeah, I think it's fine. Trying also to think of a way to do this that's efficient, so we can use a so we can create our NFA using the pattern, parse the pattern, create our NFA, and then process the string using a depth first search. However, part of the issue is excuse me, is there a way to guarantee that this isn't too slow? That's part of the problem, because if you have how many characters? I think it says 20 characters. Let me see something here. Oh, okay, basically. Oh, okay. Actually, this isn't too bad at all. So, you know, part of the issue though is that, well, actually, no, it's fine. Okay. So 2 raised to the 20. Actually, we could kind of somewhat brute force this. It's actually not. Yeah, it's not as hard as it looks. All right, how are we doing on time? I think we can actually solve this. I think so. 10 minutes. Okay. So I think the way to do this is as follows. We're going to parse our pattern to create a graph, and we're going to depth first search through that graph. Yes, it's a directed graph. It's not acyclic though. It's a directed cyclic graph. And at most, every node is going to have at most 2 edges out. The edges are going to be able to return to the same node. That's actually how we're going to implement the Kleene star part. And we're also going to have, each edge is going to have a character associated with it. And yeah, if there's only at most two branches, then our branching factor is at most 2. and this is an exponential time algorithm that we're going to write, but it's also a pretty small length for s. There is a way to convert this to, I think, quadratic time complexity rather than exponential. I wouldn't know that offhand, quite frankly. Yeah, I actually don't know. I think it's converting your NFA to a DFA. I think that's what you would do in order to achieve a more efficient result solution. But we're not going to go that far. We're going to just convert this to an NFA, and we're going to create an NFA and then process from there. So creating the NFA, so parse the pattern, generate an NFA, process the given NFA using a DFS. So parsing the pattern to generate NFA, I think we're going to have, it's actually kind of like a graph. It's going to be, we can do a vector of states, and they'll have two, we could do a vector of vectors. That's probably fine. So we have ints, and we have each vector will have another vector, should be 2 integers at most, and it's going to be, or children we'll call them, other outward edges, and those edges can go to other states. And we'll just say state machine, and we're going to say for const character C and P. We're going to have an int current state, and we're going to say also we need to actually get to the final state as well as get to the last character. Interesting. Okay. We'll come back to that. Processing, we'll come to that. So each character in the pattern will give us another state. So we're going to say state machine dot push back current state, increment the state. We're going to say if, so C is not equal to the asterisk symbol, right, because that character is a modifier. Then we do the following things. Otherwise, we have, yeah, so what we do if it is an asterisk. It's not an asterisk, then you have, we're going to say, also what is P made of? Alphanumerics, right? Or not alphanumerics, just lowercase. Okay. All right, so we don't have to worry too much about like trying to sort out like backslash characters or escape characters. So yeah, this will always be a new state. So we say, and we're going to say state machine dot back push back. I don't know, not current state. It's actually going to be. We don't actually need to increment the current state, do we? Yeah, no, we should actually. Should come back to this in a moment. Yeah, actually, I'm doing this wrong. This is probably wrong. Do we even need these? I don't think we even need these. So, yeah. So we're gonna push back on the state machine a new vector, and then or just this is fine too. And the back, we're gonna push back the character to get there. So actually, it's actually more like this. It's more like the following. So state machine push back. Actually, I have an initial state starting point, which is just a vector of integers. Initial starting point. We're going to say this is the character, and we create a new state altogether. So state 0 is just the initial state. The next state would be associated with, and there will be one what do they call that? At the initial state 0, there is one edge to the next state, and actually we need to say what the character is that'll take us to the next state, as well as where it's going to go. So it's not just integers, it's actually tuples. Character, integer, tuples. So this is going to be, for each state, you have multiple character int tuples that tell you to which state you're going to and what character is going to take you there. That's the idea. It's also, you could also make this just an unordered array, unordered map. That's probably better. I think I prefer that. Yeah, I think so. I think it's better to do an unordered map. So vectors and unordered maps. Okay. And a vector of, you can actually let the compiler figure this one out. What that's supposed to be. Just an empty vector of unordered maps. Actually, I don't think it's a vector. I think it's actually just an unordered map. I think I was wrong about that. Yeah. I think it's not a, I think it's a, each state will have an unordered map associated with it. Yes. Which is a character to int map, which gives us to which other state we can go to given a certain character. Yep. So you would say in the back of, so you would have an initial unordered map, the first state. Depending on the character, it's not an asterisk. Then you would say push back. So it's going to be back of this particular character is equal to the next state, which is going to be state machine dot size. It's really just the current size. And then you're going to push back a new state. Okay. A little confusing. And if it's anything other than asterisk, that's what you're going to add a new connection, right? If it's an asterisk though, what's going to happen is you're going to take the previous state, which you've transitioned to, and we can actually just keep track of the previous character. Yeah, no. Previous. Throw it at -1 or something. I don't know. Or you could do something like 0. Yeah, that's fine. We'll say if. So if this is taking me a while to code this here. How are we doing? 20 minutes. All right. So if previous is this value, throw an exception. We're going to leave that out. Assume correct formatting. So we're going to assume correct formatting and not add this extra branch. So if it is an asterisk, though, what that means is that our previous, we're not going to actually create this new state. We're going to take our previous character and we're going to say, we're actually going to create 2 states now. And it's going to go like this. We're going to say state machine back is going to have this previous character. So had some character, got a new state machine, and what we're going to do is actually go back one more spot, one more step, create a new jump. Is that how we're going to do this? What we want to do is take this previous character. Well, what's going to happen to this state is we have 2 things. So yeah, actually this is fine. We can do it this way. This is okay. We're going to create, okay, it's going to go like this. There's going to be a new state that we add. I'll explain in a second. So we have a jump to this current back state, and what we're going to do is we're going to say previous, whatever the previous is, it's going to go back to itself. So create a loop. Back. Most recent state. So create a loop back to the most recent state, right? And create a new state. Create an edge, a new state as well. Now this is tricky. This is called an epsilon. Where you can just jump from one state to the next. What would be better is actually to remove this so actually let me draw the graph. This is a little bit confusing. Did A star, so X star Y star Y. You'd have a state, initial state, X gets you to the new state. And then the problem is there's something happens and you get this Y And the question is, this A can actually go loop back here. So actually what I want to say is what we had originally, when we read A, we would create a new state. What we can do is actually remove that state, pop the back, and just add, yeah, we could do it that way. I think that's what we want to do. And yeah, that's fine. Pop the most recent state and added state and add a loop. Previous correct. Modify the edge. The edge moving back. So we'd say state machine dot pop back. State machine dot back of previous equals itself. -1. Yeah. This is what you'd want to do. I think this is it. So if it's not an asterisk, you can just create another state that you're hopping to. If you do see an asterisk, now you want to back up, pop the state you just created, yeah, and you could say, or you could actually just say, yeah. So you pop the previous node, pop the one you just created, and now recorrect that edge to loop back, and now now you would, and then now that would be sort of your previous node, and now the next thing you see would create a loop. And actually you can add, if you have like X star, Y star, Z star, etc., all these different characters of stars, it'll just keep creating loops on the previous node. I don't know if this doesn't work correctly actually. And the problem with this is if you did X, A star, B star, Y, this actually has issues. 30 minutes in now. So the problem is that you'd have start X, A star, which would then end up, you'd go to B. But the problem with this is that you need epsilon states, I think, because then what would happen is if you do the same processing that we just did, our B would end up here as well. But the issue is, and then you go to Y. But the issue is this, you would then be able to mix and match the A's and B's. You could pick A or you could pick B. Excuse me, which is not the case. Which is not the truth. You could pick only A a certain number of times and only B a certain number of times. So you'd have to have something more like this. and you have an epsilon jump. It's called. An epsilon jump is basically a jump that you can take without any character. You don't actually process any input, and you can just jump right there. Which is a little bit tricky how I was thinking about coding this. But now you have a, any number times a. They should create the epsilon jump then, and that creates the next state. And then, so this should be the final state. And then now b can go here, and that would have another epsilon state. Epsilon state is, yeah, right, no character to make that jump. And then finally, here you would say one more jump from this state to that y state at the end. So you could jump immediately from here to here, or from here to the last state. But you need these epsilons in between, so it makes it an NFA. Well, the NFA also, the loop, I think, makes it NFA as well. But yeah, so I guess that's fine. We can add an epsilon hop. Our epsilon hop would be excuse me. A new state with an epsilon hop. Epsilon edge. And that's going to be state machine back. This would be, it's an empty character. It's a special character. We can do something like this. Epsilon. And this would be, I don't know, we could make it like 1, some unprintable character. So we can say epsilon, and that gives you state machine.size. So all right, so this will correct the edge, and this will give you an epsilon hop to another state. Is that right? Yeah, so epsilon hop gets created first. That goes to the state machine size with size 8, and then when you push back, this index 8 would be the 9th element. Yeah, that makes sense. Yeah, that's fine. That's fine. So yeah, so you create the epsilon hop, and then right. Very interesting. Okay. So this should create our NFA, I suppose. The question now is how do we process this? So I was thinking just a simple DFS should do the trick. What's tricky though with the NFA, I guess we also need to keep track of how many characters we've used so far, our position, and then we also need to keep track of the epsilon jumps. So this could get a little hairy. Like 3 raised to the 20th is actually kind of a lot. I think we're still okay as far as timing, but it definitely gets a little bit more expensive with the epsilon jumps. So now we're going to process the given NFA using a DFS. All right, what does this look like? What does this look like? We'd start from the root node. There are two things. So first we're going to say auto DFS. We're going to do this recursively. And we're going to say, I guess, return DFS of auto F. We have a state at each point. We can take the string, that should be fine. Have int index, or just x, which is sort of the index of which character we're at that point. And we're also going to, I guess we just have the state machine as well. State machine. I should say like position, or just like state, current state, or current state. This is like the state of the state machine. We'll just say state machine state, current, or like state index. And we'll just say character index. Yeah, a little confusing, but we're gonna have base cases, and then recursion. The recursion is pretty straightforward. We're gonna say for each, so there's a state machine, and there's a state index, and we're going to say for each unordered pair there, so we say const auto reference p. We have each pair, and we're going to say if p, so we're going to say a couple things. We're going to say character x equals p dot first. And you can actually do things a little bit more complicated than that. You could say x, y. We could say c is the character and s is the next state. New state, right? Or new state index. Something like this. And we're going to say if c equals epsilon, or else if c could be epsilon, or c could be, really it's a character or epsilon, right? Those are really the only options you have. Okay. C is, it could be the dot character, or it could be any other character. Okay. So what can happen is we'll say if we're looking at epsilon, then we're going to continue our recursion without incrementing our character index. So don't touch the character index. And we update our state index, the new state index. If we're looking at any other character, then this is going to match any character in the character index. And we automatically go to that next state. Otherwise, if and only if the s of character index is equal to c, then we continue recursion there. Yeah. So that's what the dot does. It matches any character, whereas we have to match the character explicitly. And I think in this case you could just say or c equals dot. And you could do this. And then you would say, you can go so far as to say else if. I make this one branch rather than two. So else if, and otherwise you just keep going. So those are the recursion cases. Relatively straightforward. And the base cases, we're going to say, so after the recursion, I think we return false. If we, yeah, these should just return false. And we'll say return the result. Oh, no, excuse me. The way it's going to work is terminating early. So if this is the case, then return true. And similarly, if this is the case, then return true as well. So these will terminate early. Early termination. If we get to the end state, and the base cases, we're going to say if the state index is equal to if the state index is equal to the state machine dot size -1, and the character index is equal to s dot size -1, return true. So we've used all the characters in our string, and yes, it's the S is the character index, yeah. So we've used all the characters in S, and we've reached the last state. So when you get to this last state, and let's say you update this character index. Now this character index should go past the end, I want to say. Can you jump to a final state using an epsilon jump? I think so. And that won't update your character index. So it could be greater than or equal to that if we get to the ending state. Could be either of these, but it has to be greater than or equal to this. I actually think it has to be strictly this, because you didn't use all of the characters if you're not here, right? You have to use all the characters. It can't just be an epsilon jump. That's not enough. And then naturally, if state index is greater than or equal to state machine dot size, or character index is greater than the s dot size. So if you don't return true, and either of these are too large, return false. So you've gone off the edge. And then you also return false down here. And I think that's it. I think that's all you need. Initial character index is 0. Initial state index is 0. Presumably you have state to work with. Let's see if this compiles. It's ambiguous. Nice. Of course it is. All right. I realize that. Wow, I wasn't expecting it to compile. Well, I guess it didn't compile. Wrong answer. All right, which one's wrong? I actually wasn't expecting it. If it worked, I wouldn't expect anything to be wrong. So the second one. example cases are quite good. So we got false. So what happened with A is we got A connected to itself, and then with an epsilon jump to the end. And we were saying this should return true. Why does it not return true? What do we get? What happens? So we should get for each A we get another sort of branch. We have C is epsilon, so we can turn character index the new state, which is itself. So it could jump to itself any number of times. Eventually this will fail though, because the state index will keep increment. Oh no, I'm actually, excuse me, kind of. It's interesting that this actually no, it doesn't have an epsilon. It doesn't have an epsilon jump to itself. Otherwise that would loop indefinitely. Yeah, that's fine. So it would only jump to A. So character index updates. So it can jump to itself, or it could jump to the epsilon state at the end. If it jumps to the epsilon state at the end, there's nowhere to go. It just returns false. So this is just false, because it's not going to be either of these. Actually, yeah, it would be the end state, but the character index is not the right spot. So this fails immediately. Oh, excuse me, I'm doing this wrong. Oh no, it's fine. No, we're fine. Because then this would loop over each of these values in the state machine, right? Each of the pairs. So then it goes. So the epsilon state doesn't go anywhere. The next character is A. Character index 0, so it's true. This increments to the next A. New state is the same state, didn't go anywhere, or presumably. You can actually print to debug this. You can actually print. Oops. All right, how do we do here? How are we doing here? So we go through quite a few different states. We go 0, 1, 0, 1, 0. 0 is the first state, and then the first thing we do is we go to 1, and we don't return true. Then we go back to 0. We got next character. We go to 1, and we don't return true there again. And then finally we go one more value, 0. Okay. Character index is incremented, so it's off the edge. What I think is the problem you run into is this epsilon state at the end. You don't really process the epsilon state. Yeah. Part of the issue is here, right? So you don't necessarily know the order. You might process this first, and the character index, you're already over the edge. So I think that's part of the problem, is that even though you used all the characters, you have to process this epsilon edge properly, because you won't be at the right state machine. Yeah, you'll be here, and then you'll say the character index is too big, and return false. How do we deal with that properly without causing issues? Also, how are we doing on time? Yeah, still just under an hour. When you jump to the last spot, you've used all of the characters. You still want to be able to process any epsilon edges. Well, you could just do this. Else if character index is less than s.size. Or, oh, I actually need both. Yeah, so here you just fall through if the character index is already used up. We're just checking if there's this just for an epsilon check at the end. So we don't do this size check here. We don't do that size check. If we're past, well, it can't happen. Yeah, we go. That's actually impossible. Yeah, I think it's. Whew, there we go. All right, pretty good. Get rid of our debug code, I think. Let's just comment it just in case we need it for something. Alrighty, let's see. Let us see if we are successful. Hey, okay, now the question is, what if we put in like a whole bunch of so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right, we have a whole bunch of letters. I don't know. Something like this. The question is, do we time out? Do we TLE? I actually don't think we could really TLE because we're going to terminate early on in a lot of cases. Do we go for it? I think we just go for it. I don't know. There's like maybe other test cases we could use. No, I don't know. All right, let's do something kind of simple. I don't know. Just some tests, different things. Could we do like a break things? Let's do like this A for a pattern. We'll say bacon. Gotta be something I'm not thinking of here. I think we got it though. I think we're in reasonable shape. I don't know. Let's go for it. Who knows? There's probably something I missed. Very likely some kid. Oh, hey, sweet. Got there. Nice. And there's probably a more efficient way to do this. I don't know. I wouldn't know what that was offhand, what that would be offhand, but that's pretty good. That's pretty good. Not bad. Okay, I'll take it. I'll take it. I don't know. There's probably very likely a better way to do this. Who knows what that might be though, or at least as of the moment. Yeah. All right. Okay. Yeah, I don't know. Yeah. This works. Works. I don't know. I don't know what to tell you. I don't know what to say. It's kind of simple, but it works. All right. Moving on. So that's. I'm not gonna go too far into this. I mean, there's probably like we could look at the discussion and see how this might be done. How else we might want to do this. Yeah. Yeah. All right. I'm not gonna get too crazy here. Okay. Thank you for watching. Talk to you soon. I don't know what I'm doing now. Maybe I'll do another problem. Maybe not. Who knows? All right. Let me change the name of this live stream to solved. Solved. not part one, it's just one part, and that's it. Yeah, all right. Yeah, I don't know what else to say. Like we could look at the discussions, but we could also just keep going. We'll just keep going. All right, thank you for watching. Talk to you soon. Take care.